So welcome everybody. So this is 71st Flow Talk. And for those of you who are attending first time, Flow stands for Federated Learning One Word Seminar that was created as a global online forum for the dissemination of the latest scientific research results in all aspects of federated learning. And it's organized by Peter Richtárik, Virginia Smith, Aurelian Bellet, Dana Listar, myself, and Sebastian Stich. Today, it's my great pleasure to introduce you our speaker, also one of the organizer of Flow Seminar, Peter Richtárik. He's a professor of computer science at the King Abdullah University of Science and Technology at in Tuval, Saudi Arabia, and where he leads the optimization and machine learning lab. So his research interests lie at the intersection of mathematics, computer science, machine learning, optimization, numerical linear algebra, and high performance computing. And he's also one of the original developers of federated learning. And throughout his career, he's has got many awards. I think the most recent is the Best Paper Award at the NERVIPS 2020 Federated Learning Workshop. And today he's going to tell us about how local gradient step probably lead to communication acceleration. So thank you, Peter. Please go ahead.
Thank you, Samuel, for the nice introduction. And hello, everybody. It's a pleasure to give another talk here at Flow. Hopefully you're enjoying the talks, and it's nice to hear that we've had already more than 70. So today I'll talk about Proscript, which is a new algorithm, which I'll describe very slowly, so not right away, but it will take me quite a bit of time to get to what Proscript actually does. I'll try to motivate things properly. And as you can see, we have a funny title. So all of these colors, the blue and the orange and the black, all of this is part of the title. So the title is yes, and local gradient steps probably lead to communication acceleration. And finally, and yes, we have 3 exclamation marks in the title. So why do we actually have that? So we try to convey our enthusiasm about the results that we obtained. So for those of you who are not fans of strange, weird, funny, whatever you want to call this, inappropriate titles, here's a more appropriate one, more professional one: Proscript breaking the communication barrier of local gradient methods. So you can think of this as a paper that has a title and a secondary title, if you will. So this work wouldn't be possible without brilliant insights of Konstantin Mishenko, Grigory Malinovsky, and Sebastian Stich. So these are my co-authors, and Kostya and Grisha, they were and are PhD student at KAUST respectively, and Sebastian is a longtime collaborator and now assistant professor at CISPA in Germany. So as I said, I'll talk about the Proscript algorithm, but it will take me quite some time to get there, to motivate it properly. So I want to make sure that everybody understands a little bit of the history behind this method and what the method actually does. Because in fact, the method is more general than the stuff I'm going to talk about, which applies to federated learning. And I wish to take my time to motivate things properly. So introduction, let's start with gradient descent. So I understand all of you know what gradient descent is, but anyway, I have a single slide on this. So for those of you who may want to get some recollection of this. So here is gradient descent applied to the minimization of a certain 2-dimensional function. And as you can see, so in this case, the dimensionality of the problem is 2, and the function is non-convex in this case. However, in this talk, we only talk about convex, in fact, strongly convex setting. Nevertheless, the plot here is non-convex function. And gradient descent is trying to, let me turn this phone off. Gradient descent is trying to follow this path of what perhaps a river or stream of water would take down the hill. So it's a discretized method. At time t, you work with model xc, and then you subtract a multiple of the gradient of the function at that given model or iterate xc, and the multiple is sometimes called step size or learning rate, or may have some other names such as what is the other name? Okay, I just forgot the third name for this, relaxation factor. Okay, so this is gradient descent. And now let me describe the same method without any change whatsoever. It's really the same method, but I will apply it to a structured problem. And this is the main problem that people are trying to solve in federated learning. Now, there are some other variants. So let's say personalized federated learning formulations and so on and so forth, but I'll work with the one that essentially almost everybody is studying. So this is the finite sub-minimization problem, where n is the number of machines or devices, workers, clients, whatever you want to call this. And d is the dimensionality of the model you're trying to train. And Fix is the loss of the model X, which you're training on all the training data stored on client I or machine I. So in this talk, we'll not make any assumptions on the similarity of these data sets across these different clients, which is in sharp contrast with majority of works, at least early works on federated learning, where some sort of level of homogeneity or partial homogeneity or limited heterogeneity was assumed in order for the theory to make sense. So here we won't actually make any such assumptions. So now if we apply gradient descent to this problem, we want to compute gradient of the average. What is the gradient of the average? Is the average of the gradient. So gradient descent is going to look like this. So this is completely trivial. But now notice one little thing. So since the gradient of the average is the average of the gradients, while the gradient of fi of the function stored on client I can be computed by client I, the average cannot be computed by client I. It can only be computed by all the clients together, and they need to communicate in order to be able to compute this average. So this is where we get into the distributed part of gradient descent. So if you want to implement gradient descent in a distributed environment, and I'm not saying you should want to implement gradient descent, so it's a very basic method, very naive, I would say, baseline. However, most recent progress in stochastic methods for training machine learning models in general and federated learning in particular are some more elaborate, fancy versions of gradient descent. This is really why I'm talking about gradient descent. So what would distributed gradient descent look like? Let's have 3 clients or 3 workers for simplicity. Each of them contains their own data set and their own aggregate loss function F1, F2, F3, respectively. There is a server. Now, the server exists here because of the needs of communication. So this is sometimes called the orchestrating server or aggregating server, averaging server. And distributed gradient descent would look like this. So all of these workers receive a model at time t, is the same model. Now, in many practical applications, this model would in fact be compressed because the dimensionality of this model is very large. But we're going to ignore this completely because that's not what this talk is really about. Then each worker will create a copy of that model and take one step of gradient descent based on only their local function. So worker 1 subtracts multiple of gradient of f1, and notice that gradient of f1 can be computed purely based on the local data stored on worker 1. Worker 2 subtracts a multiple of gradient of f2, and so on and so forth. So the step size here is shared the same step size and constant step size for all of these clients. And after one gradient step is taken, these updated orange models or yellow models will be sent to the server. So these are d-dimensional vectors, in this case, 3 of them, and the server averages them. So why? Because the average, if you work out the algebra, is simply amounts to taking one gradient step. So this can be very easily modified, that you can think of gradient descent in this funny or in a little bit unnatural way, but it's very natural from the point of view of distributed implementation. Now, why am I rewriting this very simple method that I showed on this slide? So this one into this form and then into this complicated form, because this allows me to very easily explain what local gradient descent is. So this is really the reason. So now, after this aggregation happens, so this averaging, model xt plus 1 is obtained. It's only stored at the orchestrating server, and the server broadcasts this model back to the workers. And again, this is d-dimensional vector, so this broadcast could be expensive, but again, we're not going to be doing any compression or anything like this. We're going to handle this communication burden in a different way. And this leads us to this notion of communication efficiency. So the 6 arrows that you see here, this is what typically would be a major bottleneck of any federated learning system, because the local computation can typically be done quite quickly compared to the communication, which is orders of magnitude slower. So we need to be very careful about these arrows, the communication. And this is exactly where local gradient descent comes in as a heuristic approach to reducing the dependence of this algorithm on communication. So what is distributed local gradient descent? Well, it's almost the same method as I just described. So let's start exactly with the same steps. At iteration t, all these workers receive a copy of the same model. They create their own copy, take a gradient step. But now the idea is that don't send the updated vectors to the server at this point in time. And the reason is because maybe the computation of a single gradient is so fast, let's say a second, okay, this is just for illustration, compared to the communication with, let's say, will take a day, okay, again, I'm just imagining these numbers here. Then it looks like the system is very imbalanced. If the computation takes a second and the communication a day, obviously, this is not a good system, and maybe you should reduce the communication somehow, or maybe you should do more work before you communicate. And that's exactly what local gradient descent does. So the solution to this problem is that take another second and yet another second and so on, and take multiple gradient steps locally on all of these clients before communication. And all of these steps are gradients with respect to the local function. So let's say on client 2 or worker 2, it's always gradient with respect to function f2. In other words, each client takes capital K gradient steps starting from this green vector xt, pretending that all that the client is trying to do is minimize function f2. Okay, that's roughly really what's going on here. And then maybe these capital K steps already take a good chunk of time, so it makes sense to communicate afterwards. So then this output of all of these local gradient steps is being communicated to the server. Server does the averaging, and the average is broadcast to the workers. All right, so I'll stop here just for a second in case anybody has any questions, even though I understand this audience probably understands all of this in and out. But anyway, I'll at least sip a little bit of water.
Yes, please, if you have a question, just post it in the chat. Or
the learning rate is omitted in some parts of this equation. I can see by when, how. I don't see where it's omitted. At least not on this slide. So I can see the learning rate.
This previous page. I'll try to unmute.
The previous one, let's see. Yeah, okay, yeah. So here in the middle, the learning rate is omitted. Yeah, here in the middle.
Yes, the last line.
Yeah. So yeah, that's right. Thanks for noticing the typo. Good. All right, so this is what local gradient descent does. And now let's look a little bit back at the history of local gradient descent. So of course, all methods which have gradient in the title, they date back to at least Cauchy, which is 1847 in this paper. And then local gradient descent to some extent can be attributed to Olvi Mangasarian in his 1995 paper, Parallel Gradient Distribution Unconstrained Optimization. Is not exactly the local gradient descent as we saw here, but there's enough similarities for us to be able to attribute it to Olvi Mangasarian. But the real interest in these local gradient methods, at least from the perspective of federated learning, can be dated back to 2016, So this paper appeared online in 2016, but was published in 2017. So 2016 is when federated learning started. In this paper, Communication Efficient Learning of Deep Networks from Decentralized Data by McMahon and co-authors, where they introduced federated averaging as an algorithm for solving federated learning. And federated averaging had certain attributes, certain properties, such as partial participation of devices, stochastic approximation, and also local steps. So the local steps, that trick is the important trick which we're focusing here in this talk. We're not worried about partial participation. We're not worried about stochastic approximation. We really want to understand the nature of local steps, because this has been not understood until now, and I'll explain why. So there was this first, say, generation of local methods between 2016 and roughly 2020, where they either didn't have any analysis whatsoever. So there were heuristics which worked well to reduce the communication bottleneck in many cases, but there was no theory, or the theory had to assume that the data was essentially identical on all of these devices, or very close to being identical. So this is the homogeneous or limited heterogeneity setup. So then in 2020, so this would be a, let's say, second generation of local gradient descent methods, where the first general theory for local GD was proposed by Ahmed Khaled, Kostya Mishenka, and myself. And by general theory here, I mean general in the sense of homogeneity or heterogeneity. So no assumptions were made on the heterogeneity of the data. Unfortunately, the result here said that the method is worse than gradient descent in terms of communication efficiency. So we're happy that we had a rate for a method which was widely used in practice for a number of years, because there was no rate in the fully heterogeneous data regime prior to this work. And this, by the way, shows how young this field is. This is just a couple of years ago. But at the same time, we're disappointed that the rate was worse than gradient descent. So this is not satisfying, because in practice, the method is better very often. And here is a sample plot from this paper, which explains why in practice it's better. So this is roughly how it behaves. So notice on the x-axis, we have the number of communication rounds, and on the y-axis, we have, in some sense, distance in function values to the minimizer. And this is a strongly convex regime. So there's a unique minimizer, and we know what we're doing here. So it's a very simplified setup. So notice that if you require solution of very, very high accuracy, then taking one local step is the optimal choice, because all of these other methods, which take multiple local steps, they get stuck at a certain neighborhood of the solution. But this blue line, so this GD, gradient descent, or distributed gradient descent, that's the only one which just keeps going down and reducing the error to any precision that you might want. As soon as you introduce these local steps, all these methods start converging to some neighborhood of the solution, and the more local steps you take, the rougher the neighborhood is going to be, the bigger the neighborhood is going to be, but also the faster the initial convergence is going to be. So if you want a solution, let's say, of accuracy 10 to the power -2, then taking 32 local steps seems to be best in this case. If what you want to have solution 10 to the power -4, then this red line would be the best one. So 8 local steps, and so on. So this is where the efficiency is really coming from. However, this is not captured really by theory. And at the same time, there is this issue that of these neighborhoods. So why do we actually have to suffer convergence to a neighborhood only? So this is where the third generation of local gradient type methods comes in. And the third generation tried to handle the so-called client drift, which is what causes all of these methods not to be linearly convergent, even though gradient descent is linearly convergent. In other words, how can we remove the effect that the methods converge to a neighborhood of the solution only and not to the solution? So this is the third generation of local gradient methods. And the first one is the celebrated scaffold algorithm by Karim Reddy and co-authors. And then there were a few more. So we contributed to this effort as well, Eduard Gorgunov, Philip Hanzeli, and myself. And one of the latest papers with this kind of array is the Fedlin paper by Mitra and Cotters. So if you look at the plot on the bottom left, you will see that while LGD, which stands for local gradient descent, so the red method gets stuck at some neighborhood of the solution, roughly 10 to the power minus 4, the blue and the green methods, they just keep going down at a linear rate. So that's what you want. This is what client drift reduction actually means. However, if you compare these rates, the theoretical rates against gradient descent, we still would be disappointed. So the method no longer is sublinearly convergent in the surrounding convex regime. They are linearly convergent, all three of them, but the rate is at best equal to the rate of gradient descent, and there's no prediction coming from the theory which would say that multiple local steps actually lead to communication savings. And this is really the main problem we're trying to solve in this paper. So in other words, local gradient steps are of key importance in federated learning. They were already introduced in this paper from 2016 or 2017, whatever you want to look at it by McMahon and Cotters. It was heuristic, there was no analysis. In practice, these local steps improve communication efficiency, so you should take more than a single one. However, in theory, this is not happening. So we have one of two possibilities. Either the situation is hopeless and this heuristic simply works for sometimes, but not in the worst case. And we, let's say, only when the data is similar enough, or maybe we're still missing some pieces of the puzzle and maybe local steps help, but we need to redesign them slightly. And in fact, the latter answer is true. It turns out that yes, local steps do help. They do help in theory, and this is what we do in this paper. So without further ado here, I'll go right away to the main table that we have in the paper. So in this table, in the first row, we have gradient descent. So this is the non-local gradient descent method. You can see here in the first column, number of local steps per round is 1. The step size is 1 over L, and the rate is O tilde kappa, which means kappa is the condition number, something like Lipschitz constant of the gradient divided by strong convexity constant. And the tilde means we're omitting logarithmic factors in epsilon, in accuracy. So clearly, gradient descent is not better than gradient descent in terms of communication efficiency. And then we look at this at local GD. So this was the second generation of local gradient descent methods, which already converges without any assumption on homogeneity. However, the step sizes have to be very small on each client. So tau times smaller when tau is the number of local steps for the rate to be this provably. And this is not a linear rate. So there's 1 over epsilon times perhaps log 1 over epsilon, not in this case, depends on epsilon. So the rate is definitely not better than GD, but at least what got resolved here, as I said before, is that local gradient descent works without any assumptions on homogeneity or heterogeneity. Now there are these three methods from generation 3. These are the linearly convergent local gradient methods, which fix for the client drift. So you can see everywhere you have O tilde kappa, roughly. It's always slightly different notion of condition number, but in the best case, it would be the condition number of gradient descent. So let's say that these methods at best match the rate of gradient descent. However, they're not better than gradient descent. All of them suffer from small step sizes, 1 over tau L, 1 over tau L everywhere. So this is not complete table of all the methods out there. So some stuff I had to exclude here. And finally, we have our method, the Proscript method, which we call SCAF-new when we apply it to federated learning. And this method takes very large local step sizes, 1 over L. So the step size does not have to be decreased by the factor which is equal to the number of local steps. So this doesn't happen. And the method converges as follows. So it's also linearly convergent. So log 1 over epsilon factor is hidden in this tilde notation, but the number of communication rounds is P times kappa plus 1 over P, where P is a parameter of the method. And in particular, this is a probability scalar, something between 0 and 1, and it could be anything between 0 and 1 as long as it's strictly positive. and we can fine tune it. What does this probability mean? So probability P is the probability with which we communicate. So the probability P should be very small because we want to communicate very rarely. And we flip this coin in each iteration. So that roughly means that on expectation, each client takes 1/p local steps before communication happens. So that's what this 1/p means right here. So if you optimize now over P, this is a linear function of P, this is a convex function of P, so you can just set the derivative in P to 0. You will see that the optimal P just happens to be 1/square root of kappa. And when you choose P to be 1/square root of kappa, obviously 1/p is going to be square root of kappa. That means that the optimal number of local gradient steps is square root of the condition number. The step size is 1/L, just like gradient descent. But it turns out that the number of communication rounds is square root of kappa. So this is an acceleration of communication. So that's the result that we get. Now, if we don't know the strong convexity constant, for instance, which means we don't know the condition number, we cannot really set the probability to be equal to 1/square root of kappa. However, anytime the probability is chosen to be not too small, so larger than 1/kappa and smaller than 1, we get a communication complexity which is better than gradient descent. So this method does not necessarily require to choose to have knowledge of the strong convexity constant, but if you have that knowledge, then we can choose the probability P optimally, or in other words, we can choose the number of local steps optimally, and it'll be square root of kappa. So I'll pause here again in case anybody has any questions. And I would call this the fourth generation of local gradient methods, because this is the generation which already beats gradient descent in terms of communication efficiency.
There are no questions in chat, or I don't see any raised hands, but yeah, maybe we can wait a bit.
Yeah, so I'll just choose to wait a little bit, because in some sense, this is the most important slide, so that the main result is mentioned here. I'll mention it again after a few more minutes of some background development, but still I want to make sure that people understand
There is a question
what's going on here
from the audience. That's what K is.
So K, so let's see. So is this kappa here, or you mean the K in the local GD? There was a K there. So here this is kappa, and kappa is the condition number in this case, probably not mentioned on the slide anywhere. So kappa is something like Lipschitz constant of the gradient divided by the strong convexity constant. In fact, everywhere in this paper and in this talk, I'm assuming that we're minimizing a function that has Lipschitz gradient and that is strongly convex. So kappa is the condition number.
There's another question, so I'll try to unmute Yi. So please go ahead and ask a question.
Thank you for your presentation. I mean, the linear rate in this in the table, the linear rate does it means the algorithm will converge to the communication route. It means such as the big O 1/T.
So no, linear rate means it's in terms of number of iterations, okay, it would be exponential minus t. So 1/t would be sublinear rate. Linear rate is exponential minus t. So it's much, much faster than 1/t, and it's much faster than 1/t squared and so on. In terms of the accuracy epsilon, there will be log 1/epsilon dependence. So that's what's hidden here. So maybe we shouldn't, I mean, the table was already too wide, that's why we didn't include it, but everywhere you see the tilde, there should be times log 1/epsilon. So there's only logarithmic dependence on the error tolerance epsilon.
So you mean it will converge 1 over epsilon and
No, e to the power minus t or log 1 over epsilon. So this is the only method here which doesn't have dependence log 1 over epsilon, but it has dependence just 1 over epsilon. You can see just 1 over epsilon here. Everywhere else, there is log 1 over epsilon, but it's hidden in the tilde notation everywhere else.
Okay.
So all of these other methods are much faster than just this method. So this is the method which doesn't have any client drift correction built in. These methods have client drift correction built in, so the dependence is already much better than 1 over epsilon. It's log 1 over epsilon that's hidden in the tilde. And our methods, Proscript, shares this. But it is much better in terms of kappa, dependence on kappa, because then the dependence is square root of kappa in terms of number of communication routes. And by the way, for those of you who are confused why I call of this Proscript, and here you can see SCAFNU. So you can look at here the comment in the footnotes. So SCAFNU is actually Proscript when we apply it to federated learning. So Proscript is a more general method. I'll explain what it does. And we just decided to call it SCAFNU as a kind of new version of scaffold for federated learning.
Okay, I see. Thank you.
Okay, good. So there'll be a chance to ask these kinds of questions also later on, because I'll come back to this table one more time. So for those of you who immediately may think that, look, there's square root of condition number dependence. So this reminds people of Nesterov acceleration. In fact, if you compare Proscript to Nesterov acceleration, this is a plot by Grigori that he produced a week ago or 2 weeks ago, I don't remember exactly, where you can see that Proscript can be quite a bit faster than Nesterov acceleration. So Nesterov acceleration is not a local method. The acceleration comes from different mechanism. In Proscript, the acceleration comes from taking local steps. So in some sense, one can think of local gradient steps as being an alternative to Nesterov acceleration, an alternative mechanism that achieves the same theoretical effect, square root of kappa dependence on the condition number, in terms of the number of communication routes. However, the answer is a little bit more subtle, and I'll talk about this a little bit later on. Okay, good. So let's now go into the analysis very slowly. So the way we analyze the method is that we will not look at this problem at this.
Sorry, Peter.
level. Yeah.
There is a question from Slavo for the previous slide, I believe.
Okay. Okay. So which one was it? This one?
I think this one.
Yes. My question is that what is the function, objective function that we are minimizing?
That's an excellent question, and I have no idea. I'm assuming it's L2 regularized logistic regression, but I don't really know. This was honestly just sent to me through Slack by Grigori. He did mention what this was, but I forgot it. So I would need to ask him again or dig it out of Slack. This is not actually from the paper. This is something that he has done after the paper was put on archive.
So Grisha just confirmed that it's like L2 regularized.
And I think that mention, if I remember, is something like 144 or something like this. Maybe Grisha can comment on this if I remember from the discussion. So something like this. It was one of these libSVM data sets, and I forgot which one. Okay, so the way we actually work with federated learning is that we don't formulate the problem in this standard form of finite sum optimization, but we use a different formulation, and that formulation helps us to solve the problem. So we work with this formulation, which is a standard consensus reformulation of finite sum optimization. This is not something that we invented. There are even books that mention this kind of reformulation, but to the best of our knowledge, federated learning methods are not actually analyzed from this viewpoint. So this is completely equivalent way of writing down this problem, but the problem is suddenly lifted into much, much higher dimension, because whereas the first problem was in dimension D, the second problem is in dimension ND. So in fact, what's going on that each client is allowed to come up with arbitrary model xi. So there's no coupling or linking of these models. So each client has complete freedom to choose their own xi. And then immediately afterwards, we take the freedom away by adding a penalty, which is a drastic form of penalty, which says that you get penalized 0 if all of these models are the same and plus infinity otherwise. So you better make sure that all the models are really the same. So this is completely equivalent. And once we are there, then we can generalize this even further. So by noticing that this set, which says x1 is equal to x2 is equal to xn, is a closed convex set. So we can just say that this n tuple of d-dimensional vectors belongs to some non-empty closed convex set. And if we do this, then in fact, we're working with constraint optimization, where the constraint is a closed convex set. However, we're not stopping there. We work with yet another generalization of this formulation, where this penalty psi is an arbitrary proper closed convex function. So if you've never seen proper closed convex functions before, then you can just think of this particular function. This particular function is proper closed and convex if C is a non-empty closed convex set. So this is a function which maps this ND-dimensional vector into R and possibly plus infinity. And the function is called closed and convex if its epigraph, which is this set right here, is a closed and convex set. So these are some technicalities. I don't want to spend too much time on this. It's a standard notion from convex analysis. So in summary, instead of solving the original problem, we can solve, we'll look at this composite optimization problem at this level of generality. So minimization of a nice and smooth function and some sort of very strange non-smooth, possibly non-smooth function. Both of them, however, will be convex. So what is the right method for solving composite optimization problems? So this is a very well-studied problem. And the answer is proximal gradient descent. So what is proximal gradient descent? Well, it's a method for solving problems of this type where F we'll assume is mu convex and L smooth, which just means that this Bregman divergence is squeezed between these two quadratics, where L is the Lipschitz constant of the gradient and mu is the strong convexity constant. And the regularized, as I said, is assumed to be proper closed and convex. Here's the definition of closeness and convexity. And on top of this, we'll assume that the regularized is a proximal function, which means that the proximity or proximal operator of psi is easily computable. So ideally, there is an exact formula. You don't have to solve an optimization problem in order to compute this minimum of a quadratically perturbed version of the regularizer. Okay, so once you are in the setup, ProxGD is a method which first pretends there is no non-smooth ugly term, and you take a gradient descent step just as before with some step size. In other words, you apply the gradient operator, and after that, you apply the proximity operator. And the proximity operator, you apply to a multiple of the regularizer, and the multiple is actually the learning rate. So you just alternate gradient operator with proximal operator, or you combine them. And this is proximal gradient descent. All right, so now this is the method which you can apply to solve this general problem of minimizing F plus psi. And one thing that I wish to stress is that the proximal operator of this particular function, and I don't have a slide on this, apologize for this function, psi, which is the one that we actually use in order to work with this problem, which is the motivation for this talk, federated learning, is just the averaging operator. So you just average all of these xi's, and that's what the proximity operator does. So the proximity operator in proximal gradient descent is where the difficulty comes from in distributed implementation of gradient descent, because this means averaging, and averaging is communication, and communication is expensive. So what we ideally want to do, we want to avoid evaluating the proximity operator, because that's what is costly. And this is why the method that we design in this paper that I'm describing in this talk is called Proxskip, because it skips the proximity operator evaluations. All right, so let's look at the standard theory for proximal gradient descent. The standard theory, just like theory for gradient descent, is as follows. If the number of iterations is at least equal to the condition number, and this is the kappa from the table to the person who asked, L over mu, times log 1 or epsilon. So this log 1 or epsilon is what is hidden in these tildes in the table. Then with the largest possible step size the theory allows, 1 over L, you have solved the problem to epsilon accuracy in this relative sense. So this is the standard result. And now our result will be, for Proscript, will be essentially very, very similar, except we'll be able to achieve it with much fewer prox evaluations. So not prox evaluation every iteration, but every square root of kappa evaluations. So that's really the nature of the result. Okay, so I'll stop here again in case there are any questions, and then I'll continue to part 4. Okay, so I'll continue from here. So finally, after 40 minutes of introducing things, but hopefully I also said something about the Proscript, I'll describe the Proscript algorithm, but I'll do this in a few steps. So we asked the question, can we somehow get away with many fewer evaluations of the proximity operator in ProxGD method? And the answer is yes, and the answer is the Proscript method, but I will not show the Proscript method right away. I will first show you approach 1, which is a method which is far better than Proscript because it skips, there should be just single P here, apologies. It skips all the proxy evaluations, all of them. However, the method is not implementable at all, so it's useless. It does have one use though, because it serves as a motivation for the actual Proscript algorithm. So this is one way you can think of this method. So this method already will skip many proxy evaluations, but not all of them, but will be practically implementable. So let's look at approach 1 first. So this method is based on the following observation. Instead of minimizing f, minimize a particular linear perturbation of f, where the gradient of the linear perturbation, h star, just happens to be the gradient of the smooth part of the function at the optimum of the non-smooth problem. So x star is what we want to find, is the minimum of f plus psi, and h star is the gradient of f at x star. So if we can do this, and we can't because h star is not something that we know, but imagine if we knew h star, then in fact, x star happens to be a solution of this linearly perturbed problem because by first order optimality conditions, the solution will satisfy this equation. So you can see that x star will be a solution of this problem. So in particular, if f is strongly convex, any method applied to solving this problem will find it. However, obviously, this is not a nice reformulation because we just don't know this linear perturbation. So it's completely practically useless, and we cannot actually work with this reformulation. If we could, we skip all the proxy evaluations because notice that you can apply, for instance, gradient descent to this problem, and then gradient descent doesn't evaluate any prox of psi. So all the information, in other words, about psi is encoded in h star, and we are assuming we have knowledge of h star. So what happens when gradient descent is applied to this method? This is what happens. The gradient of linearly perturbed function is going to be a linear shift of the gradient. So this type of a method would be gradient descent applied to this linearly perturbed function. And you will see Proscript works in a very similar way. So there is a step in Proscript which looks just like this, except there's some differences as well. So this method does not evaluate any prox at all. And at the same time, as I said already multiple times, is utterly and completely useless because we don't know h star. So the idea behind Proscript from the point of view of this method would be, well, maybe we can learn this optimal shift h star iteratively. And we can learn it without evaluating prox in every single iteration. So maybe we need many fewer iterations to compute h star than the number of gradient evaluations. So in other words, we would want to have a method of this type where the shift changes and ideally converges to this optimal shift. And the method will look like this. And you can see, you will see that Proscript really looks like a method of this type. And we'll be updating HT only very rarely. And when we do, that's when we evaluate the prox of psi. So what is Proscript method? So this all motivates the Proscript method, and Proscript method looks like this. So this is something that you already seen on this slide. So it's almost the same thing. I'm just putting a hat on this point xt+1 for a reason that I'll explain. So this is the shift. These are the current model xt. And after we take this step, we flip a coin, and with some very high probability 1 minus p, we do something. And with some very small probability p, we do something else. So what do we do with high probability? Well, with high probability, we just continue. And with very small probability p, we evaluate the prox. And when we evaluate the prox, we update the shift and we update this hat vector. So that's really what's going on. So with very high probability, we do nothing. So we don't update the shift. And this hat vector just loses its hat. Okay, so we just keep doing this. In other words, with very, very high probability, Proscript just takes iterations of exactly this type. Okay, so these are iterations of the type as if you were solving this type of a problem, but you had some estimate of the shift, which you called HT, and you took many steps of gradient. Okay, so let me go back. So that's how it looks like. But with some very small probability, it does something different. And what it does, it needs to update the HT. So HT+1 is updated somehow. It needs to update the model xt+1 differently, not just by losing the hat. And it does so by evaluating the prox. And it happens the prox is evaluated in a certain way. In fact, you evaluate prox of certain multiple of the regularizer, and the multiple is really large if the probability p is very small. So you kind of compensate for the fact that you evaluate the prox very rarely by multiplying the psi by some very large number, O1/p. So this is the full Proscript algorithm if I fill in these 3 question marks. So I have the full Proscript algorithm on the next slide, but I believe this is maybe a better way of remembering what Proscript does. And here on the next slide, I will not go through this. These 3 question marks are really filled in, and I will just not talk about them. So I'll stop here again, because this is one of the most important slides in this talk.
There is one question from
Oh, hello.
Hello.
I'm reading your interesting paper, this paper. It seems that Proscript saves proximal mapping in expectation. So is there any deterministic version of Proscript that can save proximal mapping deterministically?
Okay, so I can see several interpretations of your question. So let me try to answer 2 of them. So one interpretation could be that only with some probability p, we do proxy evaluation. And this is not, let's say, after every, let's say, 10,000 steps do proxy evaluation, okay? If this is what your question means, then at the moment, there is no version of Proscript which doesn't flip coins and which evaluates the prox after a fixed number of iterations. One we don't believe that this is essential. We just believe the analysis is much simpler without such a deterministic step. And there's a precedent for this. So oftentimes when methods have this loopless structure, that there's a single loop rather than 2 loops, they're easier to analyze. But I don't believe that's really important for the method to have this kind of a rate. Your question could also mean something different, which is the final result and the nature of the final result. And maybe I'll get back to it once I actually show the main theorem.
Oh, thank you. Is it like mathematically difficult to analyze or impossible to analyze?
Well, we did not, first of all, we did not try. Okay, so when we are writing Proscript, it's not that we try to have deterministic version. we already at the start, we knew it'd be simpler with some probabilistic idea like this, because we've done research in the past where something similar was going on for very, very different methods, but something similar was going on. Let's say SVRG has 2 loops, but there's this method called loopless SVRG, which doesn't have those 2 loops, and the method is just so much simpler to analyze than SVRG. So there are precedents to this. Or there's page algorithm by Lee Jitze, who's here in the audience, and co-authors, which also uses this kind of a trick of flipping probability coin at every iteration, rather than taking certain number of local or certain number of steps in a loop, in an inner loop, and then analysis is just much simpler. But these are only analogies, because these different papers are trying to solve very different problems with very different techniques. That's nothing to do with local gradient steps. So we kind of were apprehensive of this and designed the method right away from scratch so that it would be simpler to analyze. Then we didn't want to complicate our lives.
Thank you. Thank you.
All right, so just to summarize a little bit. So this is the full Prosky method once you fill in for these 3 question marks. So again, the motivation was, if you knew this optimal shift, this one, which you don't know, then you can skip all the proxies, because you can just run gradient descent on this, and the gradient descent on this doesn't do any proxy evaluations. And if psi is the particular function that I mentioned before, that means this method would not do any communications whatsoever. But unfortunately, you cannot know the H star without any knowledge of psi. So that's why you need to be changing the H throughout. So you need to learn that optimal shift. And the way we learn it is through Proscript. And Proscript learns it through this probabilistic idea that with some very high probability does nothing, and with very low probability, it evaluates the prox and updates xt+1 and ht+1 appropriately. Okay, so Proscript theory, again, I will not spend any time on this, but I just wanted to illustrate visually that the method is very simple. Okay, so Proscript theory, just like the ProxGD theory, and this is what this theory should be compared to, is if the number of iterations is at least condition number 1/p², then you have the maximum of these 2 numbers. So remember, for ProxGD, we only had L/mu times log 1 of epsilon. Here we have the maximum of condition number n 1/p², where p is the probability of evaluating the prox. So this is the small number. Then the problem is solved to epsilon accuracy in a certain sense. Now, we don't have the distance to the minimizer. We have a Lyapunov function, psi t, which happens to be the distance to the minimizer plus some multiple of the distance between ht, the shift at iteration t, and h star, which is the optimal shift. So this theorem shows that the method Proscript actually learns the optimal shift throughout, because optimal shift, the distance between the optimal shift and the learned shift at iteration t is part of the Lyapunov function. And this suggests that indeed we're doing what I was promising we're doing. Notice though that the number of iterations is exactly the same as ProxGD if p is not too small. So if p is 1, for instance, then the maximum of these 2 numbers is going to be L/mu, just condition number. And as you start decreasing p, this 1/p² starts growing, and at some point it will have the value L/mu. And that's actually the optimal choice for p. So you should choose p small as possible, but not too small, so that 1/p² will be the dominant factor in this maximum. And precisely because we can choose p very small without this maximum exceeding L/mu, that's precisely why we can skip prox evaluations completely for free compared to ProxGD. And this is why we save in communication when we apply this to this consensus reformulation of standard federated learning problem. And this is why communication can be saved for free with local update methods, local gradient steps. Okay, so let me now optimize the expected number of proxy evaluations. What is the expected number of proxy evaluations? Well, it's just the product of the number of iterations times the probability that in any given iteration, we're going to do proxy evaluation, right? So this is just the simplest expectation ever. Number of iterations times the probability we're going to take prox evaluation. So this is the expression. If you simplify, you get this orange expression, which actually was in the table that I showed at the beginning. And now you can minimize in P this maximum of two convex functions of P. And in fact, this solution is 1/square root of the condition number. And here's a very simple visual aid supporting this. This is for a problem where the condition number happens to be 2, because then I can show the slope of this linear line is just 2. And you can see that these two lines, 1/p and 2 times p, so this is 2 times p is this, 1/p is coming from here. They intersect at this point, which is exactly 1/square root of the condition number. So this is where the maximum of these two functions, which is this and this, gets minimized. So in summary, what we get is a method which takes the same number of iterations as gradient descent, L over mu times log 1 over epsilon. However, from all of these iterations, only square root of them are communication iterations. So the expected number of prox evaluations happens to be square root of kappa times log 1 over epsilon. An expected number of gradient evaluations between two prox evaluations just happens to be square root of kappa. So if you multiply these last two lines, so this expression, that's how you get this expression. So in other words, we don't save in terms of gradient evaluations, but we save because only very few of these gradient evaluations also involve communication. Okay, so again, I stop here and I'll be happy to take any questions if there are any. Maybe I'll just go here. No questions?
No questions in the chat. No raised hands.
Okay, so I only have very few slides after this. So feel free to ask any questions about the theory if some questions arise. So I'm coming back to this table. So if you look at this expression right here, O tilde P times K plus 1/p, that's precisely coming from here. So P kappa 1/p. And I already talked about this table, so I don't have to really repeat this. And now I have a couple slides on experiments. So this slide you already seen. So Proscript can do better than next nestor of acceleration in terms of reducing the number of communication rounds, which is quite interesting to us. And there's this very interesting plot here. So maybe focus on this plot on the right. So if you set everything according to theory, so the hyperparameters such as step sizes and so on and so forth, for all of these three methods, linearly convergent local gradient methods, Fedlin, scaffold, and S-local, then you will see that they're very, very slow in terms of communication complexity compared to scaf-nu, which is Proscript applied to further learning. The gap is many orders of magnitude. You can see just many, right? Like 6 orders of magnitude or more, 8 orders of magnitude. Huge difference. And this is obvious because there's a huge difference between square root of condition number and condition number if the condition number is large, and it could be arbitrarily large, the difference. However, if you fine tune the step sizes for all of these other methods, and you go much beyond the theory, so you choose the best fixed step size in hindsight, then in fact, there's almost no difference between scaffold and scaf-nu. So you can see they're almost the same. The red and blue line here, in terms of number of communication rounds, is really the same. So there's some difference here, roughly factor of 2, because scaffold in general needs to communicate, twice a certain vector rather than once, but here, if you remove that, there's almost no difference.
I think Grisha would like to comment on something because he raised
Grisha,
hand.
please,
Let me
please,
just
please
unmute
go.
him.
Hello, can you hear me?
Yes.
I want to clarify that actually second plot is not really representative because this additional factor of 2 only needs when partial participation is used, and if not, we can use additional version of scaffold algorithm, which requires the same number of communicated vectors. So we need to, I think, remove or modify this plot.
So that's right. So this plot
this
on the
right,
right
and
makes a lot of sense. This one on the left, and this is the least important, which is why feel free everybody to just ignore it for the moment. This is not that important right now. So, and because scaffold and scafnew look almost identical in practice, as you can see, this is why we decided to call the method scafnew when applied to federated learning. So Proscript applied to federated learning is scafnew, new version of scaffold, you can think of it, and it's the version which theoretically does what it's theoretically much better, so it theoretically beats gradient descent in terms of communication complexity. Scaffold beats it practically with step sizes which are far larger than theory of scaffold allows, but scafnew does this also theoretically. All right, so there's a question.
There's also raised hand. Let me just first unmute Slavomir, and then we can take the other question.
Hi. In the beginning, in the reformulation part, you
Yes.
mentioned that there is a broader class of these proximal operators phi that or like these regularizers that are supported by the theory. And you mentioned that in order for it to be equivalent to the standard empirical risk minimization, and there is like there is this phi that it's either 0 or infinity, depending on whether all xi's are the same. Can you elaborate on what were the choices of phi in these plots?
So that's exactly the choice of psi in these plots. So we choose psi to be equal to 0 if all the x's are the same, and plus infinity otherwise, which means whenever we do prox evaluation, we're doing averaging of xi's of the local models, which means we're doing communication. So here we're really applying Proscript, as the title says, to federated learning. By this, we mean that we apply it to the consensus reformulation of federated learning. But Proscript as a method is much more general. However, we don't do experiments which are not related to federated learning in the paper.
So have you tried any other operators than this one?
We didn't have time, to be honest, to do that, but we do believe that there could be interest in trying all kinds of other expensive proximal operators, because obviously, let's say if you even work with some more general constraints, maybe the constraints don't involve communication. So the motivation for skipping proxy evaluation is not coming from communication avoidance, but it could be coming from the fact that, let's say, projection onto some polyhedral set is a complicated procedure, and you don't want to do that every step. But if you do it occasionally, rarely, you're really save a lot of time. So obviously, this Prosky procedure is far more general than explaining local steps in federated learning, and we hope that the community of researchers will look into this and try to see where else the method could be useful.
Thanks.
And then there was raised hand by Tom, but I think let me just unmute him.
Hi, Peter. Hello,
Hey,
Peter.
Tom.
Can you hear me?
I can hear you, yes.
Can you give more comments on the communication reduction? The communication reduction fact are concerned with the condition number.
Right. So let me go back right here. So so the number of communication rounds of Proscript, or let's say SCAFNU, is the same method, is square root of kappa times log1 epsilon. So this is right here in this red box, or I can show it right here in this red box. So expected number of proxy evaluations is square root of condition number times log1 epsilon. So if the condition number is million, right, then the number of communication rounds is square root of million, which is 1,000 times log1 of epsilon, depending what this is. Let's say log1 of epsilon is 5. So this would be 5,000 as opposed to 5 million, which is what ProxGD would do. So the difference is really by a factor of 1,000 if the condition number is a million. So this is a huge, huge difference in communication efficiency.
Yeah, just something come into my mind. There are some papers like the FedPD also considers this idea to skip the aggregation step.
I don't think I understood what you were saying. So I didn't hear all the words.
Okay. Oh, anyway, thank you.
All right. So apologies. I just didn't hear all the words properly. But I understood that you said something about some other papers. Well, yes, so there's lots of papers on local gradient time methods. However, as I said, none of them explain or show that the local steps actually help reducing the communication burden. Okay, but all gradient type methods, they depend on some notion of condition number. For gradient descent, it happens to be L over mu. Okay, so I had this plot. Now, there are very, very similar plots here. So you can see I'll just alternate between these two a little bit. It's almost the same stuff going on. However, here, instead of full gradients, we work with stochastic gradients. And then the method stops being linearly convergent because we don't assume the stochasticity behaves in any kind of a nice way. But still, the method is best when you compare in theory to all the other local methods. So that's this highlighted plot on the right. Again, you can ignore the plot in the middle. And on the looking at the plot on the left, you can see that scaffold and SCAFNU are pretty much leading the pack, and they're almost identical in this setup. So last two slides. So we have two extensions, which I will not talk about at all. One is from gradients to stochastic gradients. So that's what this plot was about. And we have some theory for this, but I will not talk about the theory at all. And then we have extension from fully connected network, which is one way how you can think of the setup with a single orchestrating server to arbitrary connected network, or to decentralized optimization, where there's arbitrary structure of communication links among, let's say, every two pair of clients. So either they can communicate directly or not, and then the communication only happens along the edges of this network. And there's a more general result which applies to this setup as well. Thank you very much.
Thank you, Peter, for a great talk. I see that we went a bit over time, but I don't know if you have time, maybe you can stay around for a couple of questions if there are any. Is it the case, or? Absolutely. Okay, great. So yeah, if you have questions, please just raise your hand or just post a question to chat. There's Ahmed, but just saying thanks, Peter.
Hi, Ahmed.
Maybe I would start with one question. So you at the beginning mentioned that there's like three aspects that make federated averaging like popular. One was like local steps, then stochastic approximation, and partial participation. And you showed both local steps, and now you showed the extension to stochastic approximation, so to stochastic gradients. What about partial participation? do you think that this could be satisfactorily extended to also partial participation?
So we don't know. We don't have such a result. We believe this should be possible. And we believe many things should be possible now that we are in this, let's say, generation 4 of local graded methods. And obviously we cannot do all of this. And some of these things, even if we had time, probably wouldn't solve. So we would welcome the community to look at all kinds of other extensions of Proscript. And partial participation is something that we're thinking about at the moment, but we don't have that in the paper, and it's still an open problem.
Thank you.
So the paper is on arXiv. Everybody, if you're interested in this, you can look at it. And we'll be happy to receive any feedback. Feel free to write to any of the authors or all of them. All of us will be most happy to receive any feedback. And of course, we'll be happy if you could think about any kinds of extensions or improvements or whatnot of this method.